Let's work a Raoults Law problem. Determine the vapor pressure for a solution made by mixing 25 grams of solute with 200 grams of water at 25 degrees Celsius, where the vapor pressure of pure water is 23.76 torr. Now we're going to work this problem twice, once where the solute is sucrose and one where the solute is sodium chloride, because sucrose is a covalently bound molecule and sodium chloride is ionic. And so it's going to change depending on the intermolecular forces of your compound and whether or not they break apart in solution. So you start this problem the same way you would any other problem. You define your variables and then you figure out what equations do I need to solve the problem. So this is Raoults Law. The idea that your pressure of your solution as a whole is dependent upon the partial pressure of your solvent times the typical pressure of a pure solvent. So to solve this, you're going to need your mole fraction. What do you need for mole fraction? You need to be able to convert everything into moles. So let's start out with that. So we're going to start out with 2.5 grams of sucrose, our first solute, and the molecular weight is known, that is given to you in the problem. So the molecular weight is 342.3 grams per mole. Divide this and you get 0.0730 moles of sucrose. For the mole fraction, you also need the moles of your water. So you had 200 grams of water. Multiply that by the molecular weight of water. So now we've figured out that 200 grams of water is 11.105 moles of water. And so now we can solve for our mole fraction of our solvent. Which one's our solvent? Solute, solvent. So my mole fraction of water is equal to my moles of water over my moles total, which is the sum of my moles of my sucrose and my moles of my water. And that equals 0.9935. So now I can take this mole fraction and plug it in for my mole fraction of my solvent. So my partial pressure of my solution, my total pressure of my solution equals my mole fraction times my pressure of my pure solvent, which is 23.76 torr. Plug that into your calculator and you end up with a pressure for this solution of 23.6 torr. So this is the pressure for a sucrose solution. But sucrose, when you throw it into water, it dissolves. It does not break apart. Whenever you got sodium chloride and you throw it into solution, it breaks apart. And so instead of having, for every mole of sucrose, you have 1 mole of a compound, you throw 1 mole of sodium chloride into solution and you have 1 mole of sodium and 1 mole of chlorine. It breaks apart into 2. So you end up with more moles on the bottom here in your mole fraction. So let's go ahead and do that one next. Let's see if you have 2.5 grams of sodium chloride, how much or what the pressure of that solution is. For this problem now, we already solved for the number of moles of water. Remember the symbol N? It's your moles of water. Moles is not a little m, that's mass or molality, okay? So we already learned how many moles of water we have. Now we had to convert 2.5 grams of sodium chloride into moles of sodium chloride using our molecular weight. But now what do we do with this? In order for us to put it into our mole fraction, it needs to be part over total. Well, we don't actually have any sodium chloride. All of our sodium chloride got converted into sodium ions and chlorine ions, so we don't have any of it. So if I were to redraw that chemical reaction we looked at on the previous part of this video, we would have this. Sodium chloride turns into sodium plus chlorine. So if I start out here with 0.4278 moles and none of this of each one of them, when this one gets turned into product, we're not going to have any of it left over whenever we do our reaction. So this would be like initial and this would be like final. Okay, so initially we have this, but now it's got every single sodium chloride is breaking apart. So we don't have any sodium chloride left once we've thrown it into solution. All of it has been converted here. It's 1-to-1, which means if I had 0.4278 moles of sodium chloride, I now have 0.4278 moles of sodium and 0.4278 moles of chlorine. And so I have both of these numbers of moles. And so when I'm putting it into my X here, my mole fraction, I need to make sure I include everything that's present in my solution, not things that don't exist in my solution, all right? And so how do I do this? X of water equals my moles of water, 11.105 moles of water over everything in my solution. So my water, my sodium, and my chlorine. And you will end up with different answers if you forget about that second aspect of the denominator. So we end up here with a mole fraction of 0.9285. Plug that now into Raoults Law the same way we did for sucrose, and you end up with P of our solution equal to my mole fraction times my pressure of pure water, 23.76 torr, and we end up with 22.1 torr. Okay. So basically this whole example problem hopefully should have showed you that anytime your solute is a covalently bound complex, you don't have to break it apart. You can just convert each substance into moles. If you have an ion though, you need to look at the balanced chemical equation. How does it react? Okay. If you have something that's 2 sodiums, then you need to multiply this by 2, 3 chlorines, etc. Okay. So meaning if you have something like magnesium chloride, every time this breaks apart, it produces 1 magnesium and 2 chlorine ions, which means if you start out with 1 mole here, you're going to have 1 mole of magnesium and 2 moles of chlorine. You must take that into account whenever you are looking at ionic compounds.